Hi everyone, so my name is Taylor Helfrich. This is my lab report for Lab 1. So this is a quick overview of the lab report. Feel free to pause the video if you want to look at these sections, but I'll go over them in the next couple minutes. So an introduction, the first thing is just the purpose of the lab is to first observe an object moving at a constant velocity, and then we'll actually analyze the object's motion using tracker to find the object's position versus time data. Then we'll use modeling and coding to build a computational model to accurately predict the object's position versus time data. And lastly, we'll actually compare the observed position versus time data from tracker with the predicted position versus time data from the computational model on a graph. So some of the fundamental physics principles utilized is the Newton's second law, which just relates the net interaction between system and surroundings to the observed motion of the system. As you can see below, the change in momentum over the change in time. Next, we'll talk about net force, which is just the vector sum of all the forces acting on the system. But because we're told that there is a constant velocity in this problem, we assume the net force acting on the system is 0. So all of the system forces cancel out on each other and it's in equilibrium. And the other formulas we'll use is the velocity update formula that allows us to predict the final velocity if we have data for the initial velocity, the net force, the mass, and the change in time. And same with position update formula, we can predict the future position if we have initial position, the average velocity, and change in time. And as you can see, there's a simplification of the formulas when we have an average net force of 0, which allows us to make this a little bit easier. And so a quick description of the model is that I developed it in GlowScript, and it applies Newton's second law by using the velocity update and position update formulas to compute the system's predicted position and velocity more accurately in the specified time interval. So a quick overview of results is that the computational model was very precise and accurate in predicting the system's position. So a little bit of the methodology is first, I just observed a basketball rolling across the floor of my room, took a video to see the constant velocity from the origin to the right in the positive x direction. Next, I inputted the video into Tracker, analyzed its motion using the point mass tracking feature, and then was able to get position versus time data to then calculate the basketball's initial velocity, which is also the same as constant velocity throughout the period. So then, after getting all of that data and calculating the basketball's velocity, I had all I needed to make the computational model in GlowScript. So first I created the code for visualizations and initializing the graphs. Then I created code for the system properties and initial conditions, and then plugged in the values from Tracker for the basketball mass, initial position, constant velocity, initial observation time, and size of the time step. Then I created a calculation loop in code that utilizes Newton's second law to update velocity and position at each time step, which acts just as a prediction of the position data to see how close we can get it to the actual data. So here's just some of the modeling and coding output is just the raw position versus time data, the position and velocity versus time graphs, as well as the 3D motion representation. So some results and discussion. Then we compared the observed position versus time with the predicted position versus time on a graph, and you can see they're very similar, meaning that utilizing Newton's second law as well as the velocity and position update formulas is a highly accurate way to predict an object's position at a specific time. So some differences or possible sources of error is the estimation of velocity could have been more precise, whether that's using more decimal points, and the point of mass measurements could have been more precise because it's a little difficult to tell with the human eye. And lastly, the conclusion is just the what if question. If we change the axes or flip them, we would see that the motion, displacement, and position vectors would all be in the negative x direction instead of the positive x direction, but the magnitude of these vectors would still be the same as the original. And same with velocity, that it would be in the negative x direction instead of positive x direction, but still have the same magnitude as the original. And next, the forces that are acting on this problem that add up to 0, we can split these by the axes. So for the y-axis, we have gravity in the negative y direction and normal force in the positive y direction, but they're equal in magnitude facing opposite directions, so the resulting force is net 0. And for the x-axis, we know that the object has a constant velocity, so friction force can be negligible in this situation. And since there's no acceleration, the net force in the x-axis is also 0. Thank you.